So, good evening. In our last class, we have been discussing about this IIR filter designing by impulse invariance method. We discussed that there are some disadvantages with the IIM method, impulse invariance method. And what was that? That was we had aliasing, okay, because there was many to one mapping. Okay, to overcome that, this bilinear transform method it was proposed, and it solves this problem of many to one mapping by creating a transform which creates one to one mapping. Okay, so all the analog frequencies, they are mapped into the digital frequency on a one-to-one basis. Okay, so this is the main advantage of the bilinear transform method over the impulse invariance method. Now, when we talk about this bilinear transform method, so what happens is that if you look into the bilinear transform method, it employs the transformation equation of S equals to 2 by capital T multiplied by 1 minus Z inverse divided by 1 plus Z inverse. Okay, we are not going into the details of how we derived this equation. Okay, so next let's see what is the relationship between the analog and the digital frequencies. So for that we have to take this bilinear transform method equation. S equals to 2 by capital T 1 minus Z inverse divided by 1 plus Z inverse, and if you try to rearrange it, you will find that St by 2 it is equal to Z minus 1 divided by Z plus 1. Okay, further when you try to solve it, we get to this equation 1 minus st by 2 multiplied by z is equal to st by 2 plus 1, which if you further solve it, we get that z is equal to 1 plus st by 2 divided by 1 minus st by 2. Now, in this equation, if we put the value of s over here, so we get s equal to sigma plus j omega, and if we put it we get to this equation. Okay, so in this equation if you see this sigma, it is nothing but your real component from the s plane. So we already discussed that the sigma values for the poles, it should be negative. Okay, so if it is negative, say minus of 0.5, say for example, so what happens, 1 minus something it will come divided by 1 plus something will come, so the denominator will be higher. Okay, so since denominator would be higher, what will happen, this total component modulus of z it would be less than 1, so our left hand side it is mapping within the unit circle. Similarly, if sigma is equal to 0, both numerator and denominator it becomes equal and we get 1, so our frequency axis it maps onto the unit circle. And again, if sigma is greater than 0, then what happens, your right hand side maps outside the unit circle. So it meets all the design criteria that are needed to design a stable filter. Okay, so if we now have a stable analog filter, that would easily map into the we can easily map that into the digital filter using the bilinear transform method. Okay, now what is the relationship between analog and digital frequencies? So again, we have discussed how we can find out the relationship. S will be replaced with j omega and z will be replaced with e to the power j omega. Okay, and if you do this, if you see, we get a relationship which is called omega equals to 2 tan inverse omega t by 2. Okay, omega t by 2. Now this relationship it is regarded as this frequency warping relationship. Okay, and for the analog frequency it is pre-warping relationship. omega equals to 2 by t tan of digital frequency by 2. Okay. So what does this say? This says when our analog frequency it varies from 0 to infinity, then our digital frequency it would vary from 0 to pi. Similarly, in the region negative frequency, when analog frequency is in the minus infinity to 0, our omega digital frequency it will be in the range of minus pi to 0. Okay. Now, if you plot only the positive half, we will get a straight line for the impulse invariant method. Okay. And because of that, we have seen that there was aliasing. Okay. Because there was many to one mapping. On the other hand, if you look this omega equals to 2 of tan inverse of omega t by 2, when you look into this equation which is useful in the bilinear transform method, we can see that initially there is a linear relationship. However, as we go towards the higher analog frequency components, there is a non-linear relationship. Okay. So, due to this reason, there is 1-to-1 mapping of the frequency components. Okay. So, in this way, it is stopping the aliasing. But there is a major disadvantage. And what is the disadvantage? If you look over here, in the low frequency region, we are enjoying a linear relationship. We are enjoying a linear relationship. However, as we are going towards the higher frequency components, there is a non-linear relationship. So this is one of the disadvantages. That means in the whole frequency spectrum, there is no linear, there is no single, what you call, this relationship, frequency relationship, right? In fact, what is happening in the lower regions, if you look into the frequency component, they are linearly varying. However, in the higher frequency region, due to the tan inverse function, there is a compression of the analog frequencies in the digital domain. Okay. So, the higher frequencies, they are very closely mapped. They are very closely mapped in the digital domain. Okay. So, this non-linear mapping, it is regarded as the frequency warping. Okay. So, this equation, it is related to the frequency warping. Okay. Now, what is basically happening over here? If you see here, if you consider this plot as the main plot, and then we have this relationship like this. Now, if we try to sample the analog frequency, okay, so we are sampling, see over here we are sampling, and correspondingly we are mapping the digital frequency. Now again in this region we have sampled this uh, analog frequency, and correspondingly we have found some mapping in the digital frequency, and so on. So in the whole frequency range we have done this mapping. Now in the analog thing, what is happening? If you see the amplitude modulus of h omega, it is maximally flat in both the cases, in both analog and the digital domain. However, if you look into the thickness of the frequency components in the analog domain, since we have intentionally selected a specific width of the bandwidth, so it remains the same in the analog domain. Okay, so the bandwidth or the cutout of the frequency components that we have acquired, those are same across the frequency range. However, as you go in the digital domain, in the lower frequency range, if you see, we are having the same or similar width. Okay, because at the lower frequency range, we are having linear relationship. However, as we go towards the higher frequency component, if you see in the digital domain, the frequency range has been compressed, even though we have not compressed the analog frequency in while sampling the analog frequency in the analog domain. Okay, so you can see over here that there is a marked problem over here. So there is a frequency compression at the high frequency levels, and due to this reason, if suppose in a single seat two people are sitting, right? Now if I have to demarcate between the two, it will be easier for me to segregate both of you, right? But however, if three students they sit together, then getting a demarcation, it would become quite difficult. Now again, if four students they try to fit in, now trying to segregate each component will be having a great difficulty. Okay, because within a small space we are having too many number of persons. The same thing happens over here also. Due to this non-linear relationship, what is happening, many of the frequency components they are compressed within a very short region, because when you are trying to develop the analog or this digital frequency or digital filters, what is happening, your unit circle it remains the same, right? But what is happening, within a specific region, the number of frequencies that are getting compressed, they are quite high. So designing filters in this compressed zone, in the by placing the poles and the zeros in the high frequency region, it becomes a difficult task. I am not saying it is impossible, but I am saying it becomes a difficult task. Okay, so one of the major advantage of filter designing using DLT method is the filters they have maximally flat response. Okay, they are having maximally flat response. However, their frequency distribution is non-linear. However their frequency distribution is non-linear. Okay, now with this, let us take up a couple of examples. In the first case, we have Hs equals to 2 by s plus 1 multiplied by s plus 2. So we need to convert this filter into a digital filter. It's as simple as that. We will be using this equation, bilinear transformation equation, and we will be replacing s wherever we find s with this component 2 by t multiplied by 1 minus z inverse divided by 1 plus z inverse. So we are having two s components, so we have just put these values. Okay, then we need to solve this to get the hz. Okay, similarly, let us take another example. So h of Sn, s stands to be normalized transfer function. H of Sn is equal to 1 by Sn square plus 1.414 Sn plus 1. Okay, so the cutoff frequency is given by 0.4 pi for the digital filter. So omega c is basically 0.4 pi radians per second. We will consider t equals to 1 second. Okay. Now over here, if you remember that we talked about pre-warping. Now if you see, we are having this equation. We are trying to find out the actual uh, analog frequency that we need to use for designing the filter. Okay, for designing the digital filter. So this equation, it is called pre-warping equation. Okay, so it becomes omega c equals to 2 by capital T tan of 0.4 pi by 2. Okay, so this is equal to 2 tan 0.4 pi by 2, and it comes out to be 1.453 radians per second. Okay, now we need to calculate hs. Okay, so hs can be obtained by replacing Sn by s by omega c. Okay, by replacing Sn with s by omega c. So in this equation, we will put s by omega c. Omega c we have already calculated. and we will be putting the things, and you need to solve this to get the HS. Once you have got the HS, then the simple method to put this warping, this bilinear transformation, uh, this equation over here to get the HZ, that is digital filter. Okay. So in the next class, we will be discussing about the Butterworth filter. So this is it till now. So if you have any questions, so we can discuss. Butterworth. अच्छा, इसके बाद ये. So this I have already told. I have put it so that while writing you may get mixed up. So you can read from here. So why warping occurs they have given. So this is the this result on the relationship between the analog and the digital frequency. So this is the W equal to 2 by T tan of omega D by omega dt by 2. So effects of frequency warping, as I told you, distortion of the frequency response and compression of the higher frequency components. Pre-warping, so the pre-warping formula is the same formula over here. So you have to apply it as we applied it in the second example. So that was the pre-warping we have done before implementing the filter as a digital filter. So steps in the bilinear transform method. So we need to have this analog filter specification, then substitute S with the bilinear transform, then resulting digital transfer function. In some cases, we need to apply the frequency pre-warping, which is optional. Okay, since the bilinear transformation introduces this thing, uh, so the frequencies can be adjusted pre-warped before applying the transformation. What we did in the next example, okay, to ensure accurate placement of the critical frequencies. Okay. So advantages of the bilinear transformation: avoids aliasing, wide frequency in the range mapping, and ease of application. And limitation: frequency warping, loss of angle phase characteristics, because angle and phase they are associated with the frequencies. Okay. So if you look into the comparison, bilinear transformation method, it prevents aliasing, while impulse invariance method, it cannot solve that problem. Then we have frequency range matching. So one-to-one mapping is there. In impulse invariant method, we do not have that one-to-one mapping. Then general filter type compatibility. All type of filters can be designed using the bilinear transform method. However, in impulse invariant method, we have seen that the best suited filter is the low pass filter design, right? Then accuracy in frequency response, it is uh, higher in this impulse invariance method. However, in bilinear transformation method, it is not that accurate because of the frequency warping. Then practical application, widely used in application requiring accurate frequency response characteristics such as audio processing and telecommunication, typically used where low pass filters are used. Time domain fidelity is prioritized over the frequency domain accuracy. And implementation complexity, straightforward implementation, simple but may require additional filtering to address the aliasing in the high frequency components. Okay, so with this we stop.